So, hello everybody. It's afternoon. I'm joining in from Oulu, Finland, up north. We have snow and it's -10 centigrade outdoors. It's nice to be inside and talking about Yocto and secure boot instead of being out there. So I work for Linaro. We are in the world to improve the Arm ecosystem and doing a whole bunch of stuff there. And one of these things is has a bunch to do with the secure boot. So an abstract, we will be talking about Trusted Substrate, which is an Arm SystemReady UEFI firmware that we have developed at Linaro. And also the counterpart is the operating system called Trusted Reference Stack TRS, where we have a kernel, initramfs, root file system, and so on. And all these work together with UEFI secure boot and also utilize the TPM, Trusted Platform Module, as a device to encrypt our root file systems with. And we discuss about the details of these solutions and then some of the issues that we are seeing when we try to upstream these into Yocto community layers. Yeah. So a few words. Arm SystemReady is one word which comes here and there. It's a compliance program to ensure operating system interoperability with Arm-based devices. It basically relies on the UEFI firmware standard for Arm-based devices. Then it has multiple profiles for different kinds of devices, some with more or less hardware on them and more memory and so on. And for example, the server class hardware requirements do not dictate ACPI support for the firmware, which impacts TPM discovery, which I'll briefly mention also later on. But this Arm SystemReady enables running operating systems on devices without any software modifications. So you don't need to build a device-specific software stack, or you don't need to modify or generate Linux distribution if it has been made compatible with our Arm SystemReady. It will just work on new hardware out of the box. And this is a really good for many kinds of products which don't have so strict firmware requirements. But it's also a really good starting point for devices which do have more strict boot time requirements and so on for the firmware. And there's a link to the Arm SystemReady compliance program if anyone's interested in the details. Then few words about UEFI itself. So this is Unified Extensible Firmware Interface Standard. A standard for firmware implementations, provides users and device manufacturers interfaces to run scripts to interact with the firmware and load and run binaries. And basically, one of the major points, of course, is to discover hardware which is usually not discoverable in other way. It includes support for secure boot, then some support for TPM devices as well. And there's a quite standard method for uploading new keys or vendor keys to enable secure boot with UEFI as well. And in open source world, we have a couple of common implementations that can be used for UEFI standard, and those are UBoot and EDK2. Then what is secure boot? Well, it's basically a way for the owner and maintainer or maintainer of the device to make sure that only the software that they created and signed will be able to run on the device. And basically any modification to the software that the owner or maintainer created needs to be detected, and then running the software must fail on the target. Usually it's implemented by signing the software in various ways with secure boot keys, and some of these keys may be also verified by hardware. The secure boot keys are usually not device specific, but they're generic for a range of devices or product family, or even a full-blown vendor. And as was mentioned, there are multiple layers of signing usually involved to create a chain of trust from hardware all the way up to application stack. Then TPM, or Trusted Platform Module. It's an add-on hardware module which is basically able to calculate checksums and combine them, so-called PCR values, and then these are stored on the device persistently. And the operating system that runs on the main CPU is not able to modify the data in the TPM. It's only able to amend data to these PCR data banks, but that's basically an XOR which takes the previous value and appends a new data or amends new data to it. And this can be then used to verify the boot state and to unlock access to encryption. So the use cases basically are encrypting partitions or data storage based on the boot time measurements or the full-blown boot sequence measurements. And also it can be used to block access to certain partitions data or even network services if the boot data is not cryptographically correct. And this TPM data is really specific to each device. There's usually a device-specific secret key, which is the basics of all these operations. And there's also a firmware implementation of the TPM interfaces. It's in Opti, it's called FTPM, firmware TPM, and it can be also used as an implementation if the real hardware is not available. Then measured boot. It's basically when we use the TPM device from each stage of the boot to calculate a checksum of the next sequence, for example, when we're loading binaries, and then storing this data or amending this data into the TPM. So yeah, we get a digital signature of the boot status on each of the stages that we are running in. And then this can be used to basically unlock access to device-specific data partitions, for example. Then a few words about this Linaro Trusted Substrate, which is a firmware implementation that we've done, which is compatible with Arm SystemReady IR, which is the embedded version for a number of hardware devices. We have an implementation which basically is for Arm v7 with QEMU, then Arm v8, Arm 64-bit variant of QEMU, AMD Kria KV260 without TPM support. So these QEMU devices can use a software TPM and then hook up to that. Then AMD ZCU102 as well, and RockPi 4B, Synthquasar, then Raspberry Pi 4, and also NXP's IMX8, Qualcomm's robotics platforms 1, 2, 3, and 5. Then also the Ava developer platform, which is a bigger box. And this work was done in the Linaro Ledge group, and we have sponsors who were interested in us doing this kind of a prototype. And as mentioned, a lot of these devices have also been passing and certified in the Arm SystemReady program with this firmware in the device. The basic components of the Trusted Substrate stack of firmware basically is U-boot. We take the latest one from Poky. We do some configuration changes to it though. Then we use meta-arm heavily to give us, for example, Trusted Firmware A component. And then also Opti, if we want to support Opti, for example, with the FTPM, firmware TPM on the board and in the firmware. Then we've implemented some additional features of interest for us. For example, we have the authenticated capsule updates for the firmware. I mean, when you build the firmware, you need to be able to also update the firmware. And when these updates are not cryptographically signed, then you have a security host as well. Then we've also implemented an alternative TCP/IP stack with lightweight IP into U-boot. And also this has been submitted upstream in U-boot. And that has been an enabler for enabling TLS support in U-boot directly with embed TLS, another software component which we are upstreaming into U-boot community work. And then these together enable the U-boot and UEFI interfaces to provide HTTP and HTTPS downloads. For example, to download an installer image directly in the bootloader or in U-boot or UEFI interface. Then we also have some additional ARM trusted services alternative to the TPM device, for example, to use Parsec more heavily. And of course, the basic feature that we do is this UEFI secure boot, where we verify all the binaries before we load them with the UEFI standard methodologies. Then some issues, our implementation is a proof of concept. So of course, it's not completely product ready on all aspects. We don't do the binding from the SoC firmware to the firmware, the SoC ROM, let's say, from hardware to the U-boot binary that we run, or the binary that we run. And this is because it requires very vendor-specific tooling, and it would also mean that some other aspects would be more difficult for us to work with in the CI environment, for example. So that's we use open hardware, and we also leave the device in open state so that we can use them for testing purposes. Our stack is also using private keys which are in public Git repo when we do our builds, which is of course a bad thing to do, but we do it for testing purposes. And real products will need to swap these keys to vendor keys and do the builds again. Or hopefully there's a better solution to deciding instead of embedding the keys in the Yocto build environment, but maybe I'll come back to later as well. Yeah, or there's an alternative mechanism where the keys don't need to be in the hardware at all or in the build at all, because in the UEFI firmware standard, there is a way of copying the vendor keys to the target hardware also in a separate step, which can be, for example, done after the initial production of the hardware. Then for the TLS support, the time is slightly problematic. There needs to be some notion of accurate time on the device to be able to verify certificate expirations, and that on some boards may be tricky, especially if there's no real time clock with a battery or other power management or power to the battery or clock. Yeah, and then we've enabled both U-boot and UEFI consoles by default. This is to enable our testing that we do in the Linaro Lava CI environment. And that can be used to break secure boot, and which we also do. And we just want to see that when we mess around with the TPM PCR values, then we are not able to decrypt our root file system, for example. The implementation that we have is the GitLab repo for our meta layer, which implements this. We basically have a Yocto machine configuration for each supported board. In this machine configurations, we use machine features for secure boot, which basically then does the signing and embeds the public key into the U-boot firmware binary that we can do compare that signatures then at boot time. Then we also have a machine feature for TPM too, to do the TPM measured boot support. Then also opti and capsule updates and authenticated capsule updates. For all of these, we have then machine features, which can be relatively easily enabled for also new machines. And these machine features are basically implemented by with config snippets, which are applied on top of the upstream dev config, for example, in U-boot. So we utilize for many of the boards the upstream U-boot dev config, and then we apply configuration snippets for secure boot, for TPM support, and opti, and so on top of that. And as we work really closely with the communities, our aim is to also directly right away upstream any patches that we're working with. And at least the patches that we have in the layer are, some of them which may not be merged yet, so at least they go ongoing reviews and they've been submitted already. There are some patches and changes in the layer that we are more like configuration for some of the firmware specific or hardware specific memory layouts, because we combine certain firmware elements in a way that it's basically configuration. It's not something that can be easily upstreamed because others might not be running the same opti and TPM and so on components in the firmware. And basically the build output is a binary, a firmware binary for a specific device, and which needs to be combined with the ESP partition for where the UEFI firmware then is able to load additional binaries like kernel and initramfs there. And like I mentioned, we do this testing with U-boot console a lot, so we can also make sure that when the TPM PCR values are messed with, we cannot actually access the encrypted root file system. And all tests are automated with the Linaro Lava CI setup. Yeah, so upstreaming of these features, for certain aspects we did not find a suitable upstream. For example, these devices like Rock Pi 4P, Synquazer, and AMD, and even Raspberry Pi 4. The reason is that we utilize mostly upstream U-boot and TFA and so on, and the vendor BSP layers are usually forked version, which are maybe on an older version of U-boot, where some of the issues are not fixed yet. But On the other hand, these vendor SoC and BSP layers are usually able to fix at least one major gap that we have in our secure boot world, which is when the hardware is verifying the first firmware that is executing. And we don't utilize the firmware or the vendor BSP layers so much, so that's why we don't have that enabled on all our hardware. But then again, for all the QMO machines, we found a nice upstream, which is meta-ARM, of course. And there we basically have upstreamed, and it was accepted this autumn, that we have our secure boot way of enabling it also available there on the QMO ARM secure boot machine configuration. So basically what it does is it builds U-boot-based firmware, just like in our trusted substrate stack. And then at build time, it also builds some QMO ARM poky machine definition for the kernel and also systemd boot, and then signs these with the same secure boot keys, and then creates a weak image with the ESP partition with those binaries in there. This work was upstreamed by Javier Tia from Linaro, and yeah, it's available for anyone to use. For the users of meta-ARM, they have a couple of instructions how to simply do the build, which also runs tests automatically with that the secure boot works. Here are some details of how it looks like in a CAS configuration file. For UEFI secure boot, there's a config snippet basically in meta-ARM that can be used also in other layers, I think. At the top, we basically define the keys for the secure boot signing, how to find the keys, and then there are some run QEMU related configurations. We basically need to disable run QEMU to not find the kernel directly, but instead we just put the firmware, and the firmware is supposed to load the binaries then correctly from the ESP partition. And the ESP partition is basically where the big WKS file configuration option is important. Yeah, there needs to be some config options for the systemd boot there to have some files, and then the binaries as well to load them correctly. For the machine features, yeah, we hide the UEFI secure boot behind the UEFI secure boot machine feature. So these need to be appended to the build. And we also have UEFI HCDB boot and UEFI capsule updates as machine features in meta-ARM as well now. Yeah, and then we do testing quite a bit with systemd because there are quite a few of the TPM related features are well implemented there. Yeah, maybe I'll come back to that later on as well. Yeah, and we use systemd boot, not grub, and grub is slightly problematic with TPM, and it also enables by default editing of the different boot entries, which basically is a security hole. If used correctly with TPM devices all the time, then maybe that wouldn't be such an issue because the TPM measurements would still hold correctly with grub. But in our case, we find it easier to work with systemd boot, which creates another boot entry or a menu where you can select different things to boot if you want to do that. Yeah, and like I said, systemd init is better with basically TPM, especially where the PCR measurements are done quite well already there. And we are also upstreaming the TPM support details, and the likely upstream location for those is meta security and meta-tpm layer there. I need to double check on how are with time. Okay, we need to speed up. Yeah, so then trusted reference stack from Linaro. Basically, it's the operating system counterpart where we use the same keys that were embedded into the firmware to sign the kernel, grub, or in our case, systemd boot. And then we also have the original implementation was a shell script, but we refactored this to be systemd based completely. This is to basically do all the TPM support correctly, just like basically quite a few of the existing laptops and other x86 based machines. They nowadays have UEFI as the firmware interface, and all the distros work correctly with that. Also with secure boot and TPM support. And many of the distros are based with systemd. So basically, what we create is the UEFI secure boot chain of trust. Hardware verifies the firmware. The firmware, UEFI firmware verifies systemd boot, which also is signed, and then the firmware also verifies the, let's say, UKI. We'll come back to that later, which then combines kernel command line and initial RAM disk into a single UEFI binary, which is signed correctly. So that's where we extend the secure boot all the way into the UEFI secure boot, and all the way to the initramfs. And then to bind the full root file system, we don't use the secure boot keys to sign the root file system. We instead use dm-verity, and then we embed the dm-verity hash, which is uniquely identifies the dm-verity partition into the kernel command line. So that's how we create this full chain of trust all the way to user space. Yeah. Then the same needs to be done for TPM or measurement of the boot, because the secure boot keys are generic for a bunch of devices, but we need something which is unique to a device. And TPM is the thing which is unique to a device. The TPM is a secret key. It's the first step. And then once the hardware usually has the firmware, the firmware is key measured with TPM. And then the firmware is also, when it's loading other binaries, it's measuring them into the TPM PCRs, and all the way we get into the end root file system, different measurements that can be then used to decrypt, for example, the root partition. And there are different policies and standards on which of the PCR. There are multiple PCR banks, and which of them are dedicated for which use cases. For example, one of them is basically the public key used for UEFI secure boot, that can be used as a only thing, which is then, for example, together with the device TPM device specific secret key to generate an encrypted partition key, which is unique to device. Yeah, and this is somewhat handy because it also binds the dm-verity and the dm-verity partition with the UKI binary. So hardware verifies firmware, firmware verifies UKI binary, and the UKI binary embeds the initramfs already, which is then verified, and then it also embeds the dm-verity hash, and then we have secure boot all the way. And there's an added simplification that for the software updates, the boot chain is sort of unique. When you are booting into a specific UKI, it only boots a specific dm-verity partition. And if you have updates to dm-verity partition, that means that you need to also provide a new UKI binary that is matching with the dm-verity hash on the kernel command line. Yeah, okay, the implementation, the UKI BB class was recently added into poky. It's available for anyone to use. Here's an example, which basically is in meta-ARM. It changes the meta-ARM secure boot into a UKI. And basically we have the key signing here at the top. We specify which keys to use. Then there are some QEMU boot related options. We need to disable a bunch of features because we want to boot into the firmware, and the firmware needs to find the correct things to boot directly from the ESP partition. And the ESP partition needs to be set in the VIC WKS file, which is here. And then, of course, the machine features for UEFI secure boot and so on need to be enabled. And the EFI provider needs to be systemd boot in this case. The init manager is systemd as well. And yeah, then we add a bunch of tests, image classes for UKI, and of course with UKI, because we're binding the kernel initramfs and kernel command line into on the one side secure boot side binary, we also need to build an initramfs, which in our case is core image minimal initramfs. And then the SP sign classes here are basically to get access to the keys, which are actually being used by the UKI tooling from systemd to handle the signing. Yeah. Yeah, so then a whole bunch of small issues and details around systemd and initramfs. I think in our case, it's best to implement all of these. They all use systemd already in the initramfs, which is not correctly the default in any of the poky or other image recipes. We need to maybe provide an example, and that's where we're working on upstreaming this solution as well. And so there are certain details, for example, that the actually I will skip this slightly. just to save time. We're running out of it already. Then there's a whole bunch of details around using dm-verity correctly and combining that, for example, with weak images, which are doing other stuff. So, for example, in our prototype environment, we had to split the dm-verity work, which is basically dm-verity support comes from meta-security. But the way that we use it, it's not so easy to combine it with other images, especially weak images. And we had to split the main root file system to a different recipe, which creates both a root file system and the UKI binary, and then also the initramfs. And then an actual recipe for the image, which then creates the end weak image file. And this was because some issues in that, because the dm-verity classes in meta-security are also generating a weak image configuration, and these were conflicting with each other. And we're planning to upstream these so that we have a running system also, or anyone can test this out more easily. Then other issue that we've especially run into was the firmware TPM support, because it also has a dependency to T-supplicant, which is a userspace component of the Opti software stack. And that has a dependency to replay protected memory block to basically store data securely for the TPM. And all of these had a quite complicated dependency tree, which meant that in the initramfs you need to also start the T-supplicant before the actual init to make the firmware TPM device usable. Luckily, some developers, Jens Wiklander in our case, was already working on a solution which basically moves the RPMB support implementation directly into kernel. And this is available now in upstream kernel 6.12 already. And that removes the need to run the T-supplicant completely from the initramfs when working with a firmware TPM device. Details, but the majority of the work has been done in the kernel support for RPMB access. Which was tricky because so tricky to solve is how to basically detect the TPM device. The logic on systemd currently is twofold. First of all, if there is already a TPM device when systemd runs, which is the first thing, for example, in an initramfs, then it means that the kernel driver was already built into the kernel and it's detected and working correctly. The other alternative for systemd to know that there is a TPM device is that if there is an ACPI table entry for in the firmware, which is exported through the kernel to systemd. And then if this happens, then systemd knows that, okay, we need to wait for a TPM device to appear. But this breaks if the TPM support is compiled into the kernel as modules, which are not loaded before the systemd init runs, which is basically before UDEV. And also, what if the devices don't have ACPI support, like the Arm SystemReady IR, which basically tries to embed everything into device tree instead of ACPI. And for these cases, we basically have a prototype patches available, which have not been merged yet. But anyway, there's, for example, a way for the TPM devices to export some event logs from the firmware to the operating system. And the kernel UEFI stuff does this and receives those, but they are not visible in user space at all at the moment. So if those are exported to user space, then systemd can use that also as a way to detect that there is a TPM device. And then it can also then queue in the user space portions of the TPM stack. Right. Somewhat related is the partition auto detection stuff, but maybe I'll skip this. I mean, it becomes easier when security is included, but if you don't have security like dm-verity, then it's a bit tricky how to detect a partition before when at build time. The reason, or one of the solutions is there to use these global standards for GUIDs, where you can generate the partition which systemd is automatically able to detect as the root file system, as a dm-verity root file system, or a dm-verity user partition. These are really handy to have there. And of course, testing had some issues as well, a whole bunch of details there. Testing on x86 versus our native ARM machines is somewhat tricky. There are some bugs somewhere in KVM or somewhere that made at least upstreaming of the UKIPP class quite complicated. We had to do several iterations, and Richard was at least tirelessly running the test, which was good. And finally, we got it working correctly. And then another silly side effect is that on some build and test cases, I suddenly had an empty root file system, which was really annoying, but it turns out to be just a simple issue of using BP fatal in a test image BP class. Here's a link to the actual commit, which downgrading the BP fatal to error somehow magically resolved the issue. Yeah, so quite frequently when we're upstreaming changes, we run into all kinds of issues which we had no idea that would become blockers for the thing. And one of the issues which is also really unsolved is how to manage keys in the bitbake build or any way in the build. I mean, there's the HSM, high security module hardware, or the software variant of that, or like currently meta-secure core, meta-arm, we are basically hacking the keys into the build system using environment variables and so on, and this isn't good for build reproducibility. Yeah, I hope someone would tackle this solution and document it really well. So. And I hope I'm sufficiently, we are working on these issues for a long time, and I think maybe in 2025 we've had these solutions for secure boot, both the firmware and the operating system part end-to-end covered in some use case in one of the Yocto layers. And yeah.